Uniform Vec3 I resolution, /. F names for uniforms. For example, shadertoy.com uses the same uniforms but with the following names. The Book of Shaders by Patricio Gonzalez. The #ifdef gl_s precision medium float #ndif uniform vec2 u_resolution / canvas size width height uniform vec2 u_ mouse / mouse position in screen pixels uniform float u_time / time in seconds since load. You can picture the uniforms like little bridges between the CPU and the GPU. The names will vary from implementation to implementation, but in this series of examples I'm always passing u_time, time in seconds since the shader started, u_resolution, billboard size where the shader is being drawn, and u_mouse, mouse position inside the billboard in pixels. I'm following the convention of putting u_ before the uniform name to be explicit about the nature of this variable, but you will find all kinds of names for uniforms. For example, shadertoy.com uses the same uniforms but with the following names. Uniform Vec3 I resolution, / viewport resolution, in pixels, uniform Vec4 I mouse, / mouse pixel chords. XY, current, ZW, click uniform float I time, / shader playback time, in seconds. Enough talking, let's see the uniforms in action. In the following code we use u_time, the number of seconds since the shader started running, together with a sine function to animate the transition of the amount of red in the billboard. As you can see, GLSL has more surprises. The GPU has hardware accelerated angle, trigonometric and exponential functions. Some of those functions are sine, cosine, tan, asyn, acos, aton, POW, exp, log, sqrt, abs, sine, floor, seal, fract, mod, minute, max, and clamp. Now it is time again to play with the above code. Slow down the frequency until the color change becomes almost imperceptible. Speed it up until you see a single color without flickering. Play with the 3 channels, RGB, in different frequencies to get interesting patterns and behaviors. GL_frag chord. In the same way GLSL gives us a default output, vec4 gl_frag color, it also gives us a default input, vec4 gl_frag chord, which holds the screen coordinates of the pixel or screen fragment that the active thread is working on. With vec4 gl_frag chord, we know where a thread is working inside the billboard. In this case we don't call it uniform because it will be different from thread to thread, instead gl_frag chord is called a varying. In the above code we normalize the coordinate of the fragment by dividing it by the total resolution of the billboard. By doing this the values will go between 0.0 and 1.0, which makes it easy to map the X and Y values to the red and green channel. In Shaderland we don't have too many resources for debugging besides assigning strong colors to variables and trying to make sense of them. You will discover that sometimes coding in GLSL is very similar to putting ships inside bottles. Is equally hard, beautiful and gratifying. Now it is time to try and challenge our understanding of this code. Can you tell where the coordinate 0.0, 0.0 is in our canvas? What about 1.0, 0.0, 0.0, 1.0, 0.5, 0.5, and 1.0, 1.0? Can you figure out how to use u_mouse knowing that the values are in pixels and not normalized values? Can you use it to move colors around? Can you imagine an interesting way of changing this color pattern using u_time and u_mouse coordinates? After doing these exercises you might wonder where else you can try your new shader powers. In the following chapter we will see how to make your own shader tools in 3.js, processing, and open frameworks. The Book of Shaders by Patricio Gonzalez. Turn on the lights. Running your shader. As part of the construction of this book and my art practice, I made an ecosystem of tools to create, display, share, and curate shaders. These tools work consistently across Linux, macOS, Windows, and Raspberry Pi and browsers without the need of changing your code. Running your shaders on the browser. Display. All live examples in this book are displayed using GLSL Canvas, which makes the process of running standalone shader incredibly easy. Canvas class equals GLSL Canvas data fragment URL equals your shader.frag data textures equals your input image.png width equals 500 height equals 500 canvas. As you can see, it just needs a canvas element with class equals GLSL Canvas and the URL to your shader in the data fragment URL. Learn more about it here. If you are like me, you will probably want to run shaders directly from the console. In that case you should check out GLSL Viewer. This application allows you to incorporate shaders into your bash scripts or Unix pipelines and use it in a similar way to ImageMagick. Also, GLSL Viewer is a great way to compile shaders on your Raspberry Pi, which is the reason OpenFrame.io uses it to display shader artwork. Learn more about this application here. GLSL Viewer your shader.frag your input image.png W500H500E screenshot, your output image.png. Create. In order to illuminate the experience of coding shaders, I made an online editor called GLSL Editor. This editor is embedded on the book's live examples. It brings a series of handy widgets to make more tangible the abstract experience of working with GLSL code. You can also run it as a standalone web application from editor.thebookofshaders.com. Learn more about it here. If you prefer to work offline using Sublime Text, you can install this package for GLSL Viewer. Learn more about it here. Share. The online editor, editor.thebookofshaders.com, can share your shaders. Both the embedded and standalone version have an export button where you can get in unique URLs to your shader. Also, it has the ability to export directly to an openframe.io. Curate. Sharing your code is the beginning of you sharing your shader as artwork. Beside the option to export to openframe.io, I made a tool to curate your shaders into a gallery that can be embedded on any site. Its name is GLSL Gallery. Learn more here. Running your shaders on your favorite framework. In case you already have experience programming in a framework like Processing, 3.js, OpenFrameworks, or SFML, you're probably excited to try shaders on these platforms you feel comfortable with. The following are examples of how to set shaders in some popular frameworks with the same uniforms that we are going to use throughout this book. In the GitHub repository for this chapter, you'll find the full source code for these 3 frameworks. In 3.js, the brilliant and very humble Ricardo Cabello, aka Mr. Doob, has been developing along with other contributors probably one of the most famous frameworks for WebGL, called 3.js. You will find a lot of examples, tutorials, and books that teach you how to use this JavaScript library to make cool 3D graphics. Below is an example of the HTML and JS you need to get started with shaders in 3.js. Pay attention to the ID equals fragment shader script. Here is where you can copy the shaders you find in this book. Body div ID equals container div script src equals js 3.minute js script ID equals vertex shader type equals x shader x vertex void main gl underscore position equals vec4 position 1.0 script ID equals fragment shader type equals x shader x fragment uniform vec2 u underscore resolution uniform float u underscore time void main vec2 st equals gl underscore fragchord xy u underscore resolution xy gl underscore frag color equals vec4 stx sty 0.0 1.0 script var container, var camera, scene, renderer, clock, var uniforms, init, animate, function init, container equals document.getElementById, by ID, container, camera equals new3.camera, camera.position z equals 1, scene equals new3.scene, clock equals new3.clock, var geometry equals new3.planebufferGeometry, 2, 2. Uniforms equals, u underscore time, type. F, value, 1.0, u underscore resolution, type, v2, value, new3.vector2, u underscore mouse, type, v2, value, new3.vector2, var material equals new3.shader material, uniforms, vertex shader, document.getElementById, vertex shader, text content, fragment shader, document.getElementById, fragment shader, text content, var mesh equals new3.mesh. Geometry, material, scene.add, mesh, renderer equals new3.webgl renderer, renderer.setPixel ratio, window.device pixel ratio, container.appendChild, renderer.DOMElement, on window resize, window.addEvent listener, resize, on window resize, false, document.onMouseMove equals function, e. Uniforms.u underscore mouse.value.x equals e.pagex uniforms.u underscore mouse.valued y equals e.page y. Function on window resize, event, renderer.setSize, window.innerWidth, window.innerHeight, uniforms.u underscore resolution.valued x equals renderer.DOMElement.width, uniforms.u underscore resolution.valued y equals renderer.DOMElement.height, function animate, request animation frame, animate, render, function render, uniforms.u underscore time.value plus equals clock.getDelta, renderer.render, scene, camera, script furious smiley body. In processing. Started by Ben Fry and Casey Rears in 2001, processing is an extraordinarily simple and powerful environment in which to take your first steps in code. It was for me at least. Andres Kalubri has made important updates to the OpenGL and video in processing, making it easier than ever to use and play with GLSL shaders in this friendly environment. Processing will search for the shader named shader.frag in the data folder of the sketch. Be sure to copy the examples you find here into that folder and rename the file. pShader void setup, size, 640, 360, p2d, no stroke, shader equals load shader, shader.frag, void draw, shader.set, u underscore resolution, float, width, float, height, shader.set, u underscore mouse, float, mousex, float, mousey, shader.set, u underscore time, millis, 1000.0, shader, rect, 00 width height. In order for the shader to work on versions previous to 2.1, you need to add the following line at the beginning of your shader, #define processing underscore color underscore shader, so that it looks like this. #ifdef gl underscore s precision medium float, #endif #define processing underscore color underscore shader uniform vector. The Book of Shaders by Patricia. Algorithmic drawing. Shaping functions. This chapter could be named Mr. Miyagi's fence lesson. Previously, we mapped the normalized position of x and y to the red and green channels. Essentially, we made a function that takes a two-dimensional vector, x and y, and returns a four-dimensional vector, r, g, b, and a. But before we go further transforming data between dimensions, we need to start simpler, much simpler. That means understanding how to make one-dimensional functions. The more energy and time you spend learning and mastering this, the stronger your shader karate will be. The Karate Kid, 1984. The following code structure is going to be our fence. In it, we visualize the normalized value of the x-coordinate, stx, in two ways. one with brightness, observe the nice gradient from black to white, and the other by plotting a green line on top. In that case the x value is assigned directly to y. Don't focus too much on the plot function, we will go through it in more detail in a moment. Quick note. Note, the Vec3 type constructor understands that you want to assign the 3 color channels with the same value, while Vec4 understands that you want to construct a 4-dimensional vector with a 3-dimensional 1 plus a 4th value, in this case the value that controls the alpha or opacity. See for example lines 19 and 25 above. The Vec3 type constructor understands that you want to assign the 3 color channels with the same value, while Vec4 understands that you want to construct a 4-dimensional vector with a 3-dimensional 1 plus a 4th value, in this case the value that controls the alpha or opacity. See for example lines 19 and 25 above. This code is your fence, it's important to observe and understand it. You will come back over and over to this space between 0.0 and 1.0. You will master the art of blending and shaping this line. This one-to-one relationship between x and y, or the brightness, is known as linear interpolation. From here we can use some mathematical functions to shape the line. For example, we can raise x to the power of 5 to make a curved line. Interesting, right? On line 22 try different exponents, 20.0, 2.0, 1.0, 0.0, 0.2, and 0.02 for example. Understanding this relationship between the value and the exponent will be very helpful. Using these types of mathematical functions here and there will give you expressive control over your code, a sort of data acupuncture that lets you control the flow of values. POW is a native function in GLSL and there are many others. Most of them are accelerated at the level of the hardware, which means if they are used in the right way and with discretion they will make your code faster. Replace the power function on line 22. Try other ones like exp, log, and sqrt. Some of these functions are more interesting when you play with them using pi. You can see on line 8 that I have defined a macro that will replace any use of pi with the value 3.14159265359. Step and smooth step. GLSL also has some unique native interpolation functions that are hardware accelerated. The step, interpolation receives 2 parameters. The first one is the limit or threshold, while the second one is the value we want to check or pass. Any value under the limit will return 0.0 while everything above the limit will return 1.0. Try changing this threshold value on line 20 of the following code. The other unique function is known as smooth step. Given a range of 2 numbers and a value, this function will interpolate the value between the defined range. The 2 first parameters are for the beginning and end of the transition, while the third is for the value to interpolate. In the previous example, on line 12, notice that we've been using smooth step to draw the green line on the plot function. For each position along the x-axis this function makes a bump at a particular value of y. How? By connecting 2 smooth step together. Take a look at the following function, replace it for line 20 above and think of it as a vertical cut. The background does look like a line, right? Float y equals smooth step, 0.2 0.5 stx, smooth step, 0.5 0.8 stx. Sine and cosine. When you want to use some math to animate, shape or blend values, there is nothing better than being friends with sine and cosine. These 2 basic trigonometric functions work together to construct circles that are as handy as MacGyver's Swiss Army knife. It's important to know how they behave and in what ways they can be combined. In a nutshell, given an angle, in radians, they will return the correct position of x. X, cosine, and y, sine, of a point on the edge of a circle with a radius equal to 1. But, the fact that they return normalized values, values between -1 and 1, in such a smooth way makes them an incredible tool. While it's difficult to describe all the relationships between trigonometric functions and circles, the above animation does a beautiful job of visually summarizing these relationships. Take a careful look at this sine wave. Note how the y values flow smoothly between +1 and -1. As we saw in the time example in the previous chapter, you can use this rhythmic behavior of sin to animate properties. If you are reading this example in a browser, you will see that you can change the code in the formula above to watch how the wave changes. Note, don't forget the semicolon at the end of the lines. Try the following exercises and notice what happens. Add time, u_time, to x before computing the sin. Internalize that motion along x. Multiply x by pi before computing the sin. Note how the 2 phases shrink so each cycle repeats every 2 integers. Multiply time, u_time, by x before computing the sin. See how the frequency between phases becomes more and more compressed. Note that u_time may have already become very large, making the graph hard to read. Add 1.0 to sin, x. See how all the wave is displaced up and now all values are between 0.0 and 2.0. Multiply sin, x, by 2.0. See how the amplitude doubles in size. Compute the absolute value, abs, of sin, x. It looks like the trace of a bouncing ball. Extract just the fraction part, fract, of the resultant of sin, x. Add the higher integer, ceil, and the smaller integer, floor, of the resultant of sin, x, to get a digital wave of 1 and -1 values. Some extra useful functions. At the end of the last exercise we introduced some new functions. Now it's time to experiment with each one by uncommenting the lines below one at a time. Get to know these functions and study how they behave. I know, you are wondering, why? A quick Google search on generative art will tell you. Keep in mind that these functions are our fence. We are mastering the movement in 1 dimension, up and down. Soon, it will be time for 2, 3, and 4 dimensions. Anthony Mattox, 2009. Advanced Shaping Functions. Golan Levin has great documentation of more complex shaping functions that are extraordinarily helpful. Porting them to GLSL is a really smart move to start building your own resource of snippets of code. Polynomial shaping functions, www.eflong.com/archive/texts/code/shapers_poly. Exponential shaping functions, www.eflong.com. Circular and elliptical shaping functions, Bezier and other parametric shaping functions, www.eflong.com. 2016. Quadratic Bezier. Oh. @kindinfo 2016. Cubic Bezier. Oh. @kindinfo 2016. Cubic Bezier through 2 points. Oh. Like chefs that collect spices and exotic ingredients, digital artists and creative coders have a particular love of working on their own shaping functions. Inigo Quiles has a great collection of useful functions. After reading this article, take a look at the following translation of these functions to GLSL. Pay attention to the small changes required, like putting the dot on floating point numbers and using the GLSL name for C functions. For example, instead of POW, use POW. Inigo Quiles. Impulse. Oh. Inigo Quiles. Cubic pulse. Oh. Inigo Quiles. Expo. Oh. Inigo Quiles. EXP step. Oh. Inigo Quiles. Parabola. Oh. Inigo Quiles. P-curve. Oh. To keep your motivation up, here is an elegant example, made by Dangwafer, of mastering the shaping functions karate. In the next chapter we will start using our new moves. First with mixing colors and then drawing shapes. Exercise. Take a look at the following table of equations made by KYND. See how he is combining functions and their properties to control the values between 0.0 and 1.0. Now it's time for you to practice by replicating these functions. Remember, the more you practice the better your karate will be. KYND www.flickr.com/photos for your toolbox. LYGIA is a shader library of reusable functions that can be included easily on your projects. It's very granular, designed for reusability, performance, and flexibility, and can easily be added to any projects and frameworks. It's divided in different sections and it have an entire one for math operations. GraphToy. Once again, Inigo Quiles made a tool to visualize GLSL functions in WebGL. Inigo Quiles, GraphToy, 20. The Book of Shaders by Patricio Gonzalez Vivo and Jen Lo. Bahasa Indonesia, Tingvit, Español, Portuguese, Francais, Italiano, Deutsch, Polski, English. Turn on the lights. Paul Klee, Color Chart, 1931. Colors. We haven't much of a chance to talk about GLSL vector types. Before going further, it's important to learn more about these variables, and the subject of colors is a great way to find out more about them. If you are familiar with object-oriented programming paradigms, you've probably noticed that we have been accessing the data inside the vectors like any regular C-like struct. Vec3 red equals vec3, 1.0, 0.0, 0.0, red text equals 1.0, red y equals 0.0, red z equals 0.0. Defining color using an x, y, and z notation can be confusing and misleading, right? That's why there are other ways to access this same information, but with different names. The values of .x, .y, and .z can also be called .r, .g, and .b, and .s, .t, and .p, .s, .t, and .p are usually used for spatial coordinates of a texture, which we'll see in a later chapter. You can also access the data in a vector by using the index position, 0, 1, and 2. The following lines show all the ways to access the same data. Vec4 vector 0 equals vector r equals vector x equals vectors, vector 1 equals vector g equals vector y equals vector t, vector 2 equals vector b equals vector z equals vector p, vector 3 equals vector dot a equals vector dot w equals vector dot q. Q. These different ways of pointing to the variables inside a vector are just nomenclatures designed to help you write clear code. This flexibility embedded in shading language is a door for you to start thinking interchangeably about color and space coordinates. Another great feature of vector types in GLSL is that the properties can be combined in any order you want, which makes it easy to cast and mix values. This ability is called swizzle. Vec3 yellow, magenta, green, / making yellow yellowed RG equals vec2, 1.0, / assigning 1. To red and green channels yellow, 2, equals 0.0, / assigning 0. To blue channel // making magenta equals yellow.rbg, // assign the channels with green and blue swapped // making green.rgb equals yellow.bgb, // assign the blue channel of yellow, 0, to red and blue channels. Mixing color. Now that you know how colors are defined, it's time to integrate this with our previous knowledge. In GLSL there is a very useful function, mix, that lets you mix two values in percentages. Can you guess what the percentage range is? Yes, values between 0.0 and 1.0. Which is perfect for you. After those long hours practicing your karate moves with the fence, it is time to use them. Check the following code at line 18 and see how we are using the absolute values of a sin wave over time to mix color A and color B. Show off your skills by. Make an expressive transition between colors. Think of a particular emotion. What color seems most representative of it? How does it appear? How does it fade away? Think of another emotion and the matching color for it. Change the beginning and ending color of the above code to match those emotions. Then animate the transition using shaping functions. Robert Penner developed a series of popular shaping functions for computer animation known as easing functions. You can use this example as research and inspiration, but the best result will come from making your own transitions. Playing with gradients. The mix function has more to offer. Instead of a single float, we can pass a variable type that matches the two first arguments, in our case a vec3. By doing that we gain control over the mixing percentages of each individual color channel, R, G, and B. Take a look at the following example. Like the examples in the previous chapter, we are hooking the transition to the normalized x-coordinate and visualizing it with a line. Right now all the channels go along the same line. Now, uncomment line number 25 and watch what happens. Then try uncommenting lines 26 and 27. Remember that the lines visualize the amount of color A and color B to mix per channel. You probably recognize the three shaping functions we are using on lines 25 to 27. Play with them. It's time for you to explore and show off your skills from the previous chapter and make interesting gradients. Try the following exercises. William Turner, The Fighting Temeraire, 1838. Compose a gradient that resembles a William Turner sunset. Animate a transition between a sunrise and sunset using u_time. Can you make a rainbow using what we have learned so far? Use the step function to create a colorful flag. HSB. We can't talk about color without speaking about color space. As you probably know, there are different ways to organize color besides by red, green, and blue channels. HSB stands for hue, saturation, and brightness, or value, and is a more intuitive and useful organization of colors. Take a moment to read the RGB2 HSV and HSV2 RGB functions in the following code. By mapping the position on the x-axis to the hue and the position on the y-axis to the brightness, we obtain a nice spectrum of visible colors. This spatial distribution of color can be very handy. It's more intuitive to pick a color with HSB than with RGB. HSB in polar coordinates. HSB was originally designed to be represented in polar coordinates, based on the angle and radius, instead of Cartesian coordinates, based on x and y. To map our HSB function to polar coordinates, we need to obtain the angle and distance from the center of the billboard to the pixel coordinate. For that we will use the length function and aton, yx, which is the GLSL version of the commonly used aton2, yx. When using vector and trigonometric functions, vec2, vec3 and vec4 are treated as vectors even when they represent colors. We will start treating colors and vectors similarly. In fact, you will come to find this conceptual flexibility very empowering. Note, if you were wondering, there are more geometric functions besides length like distance, dot, cross, normalize, face forward, reflect, and refract. Also, GLSL has special vector relational functions such as less than equal, greater than equal, and not equal. Once we obtain the angle and length, we need to normalize their values to the range between 0.0 to 1.0. On line 27, aton, yx, will return an angle in radians between pi and pi, minus 3.14 to 3.14, so we need to divide this number by tw_pi, defined at the top of the code, to get values between minus 0.5 to 0.5, which by simple addition we change to the desired range of 0.0 to 1.0. The radius will return a maximum of 0.5, because we are calculating the distance from the center of the viewport, so we need to double this range, by multiplying by 2, to get a maximum of 1.0. As you can see, our game here is all about transforming and mapping ranges to the 0.0 to 1.0 that we like. Try the following exercises. Modify the polar example to get a spinning color wheel, just like the weighting mouse icon. Use a shaping function together with the conversion function from HSB to RGB to expand a particular hue value and shrink the rest. William Home Lizar's red, blue and yellow spectra, with the solar spectrum, 1834. If you look closely at the color wheel used on color pickers, see the image below, they use a different spectrum according to RYB color space. For example, the opposite color of red should be green, but in our example it is cyan. Can you find a way to fix that in order to look exactly like the following image? Hint, this is a great moment to use shaping functions. Read Joseph Albus' book Interaction of Color and use the following shaders examples as practice. Interaction of color 4. Interaction of color 4. Interaction of color 4. Interaction of color V. Interaction of color V. Interaction of color 6. Interaction of color 7. Note about functions and arguments. Before jumping to the next chapter, let's stop and rewind. Go back and take a look at the functions in previous examples. You will notice in before the type of the arguments. This is a qualifier, and in this case it specifies that the variable is read-only. In future examples we will see that it is also possible to define arguments as out or in-out. This last one, in-out, is conceptually similar to passing an argument by reference, which will give us the possibility to modify a passed variable. Int new function, in vec4 of vec4, // read only out vec3 of vec3, // write only in out int ain't, // read write. You may not believe it, but now we have all the elements to make cool drawings. In the next chapter we will learn how to combine all our tricks to make geometric forms by blending the space. Yep, blending the space. For your toolbox. LYGIA's color shader functions are set of reusable functions to manipulate colors in GLSL. It includes functions to convert between color spaces, to blend colors, to create gradients, and to apply color transformations. It's very granular library, designed for reusability, performance, and flexibility, and it can be easily be added to any projects and frameworks. Previous. Home. Next. Copyright 2015 Patricio Gonzalez Vivo.